Okay, student. Now, so this is the PD controller. Now again I will take one plant. Okay. Now this is 1 by S into. First we will see without controller. Now this is type is 1, means somewhat error is more because type is less, and the characteristic equation is one by S into S plus 10. So characteristic equation is S square plus 10S plus 1 equal to 0, S square plus 2 zeta omega n into S plus omega n square equal to 0, right? So where this is already you know omega n equal to 1 radians per second and 2 zeta omega n which is equal to 10. So zeta which is equal to 5 and zeta which is greater than 1. So when zeta greater than 1, overdamped response, poles are not repeated on the negative real axis, system is stable. So this is without control. Now what we are doing? Now here system is stable, but error is somewhat less. Sorry, error is somewhat more. But that error is already decreased by using one single controller, is called as I controller. But I controller decrease the error, system will become unstable. So now I will take the combination of I. So now with PI controller, okay, with PI controller. So proportional plus integral controller, PI controller, P plus I controller, proportional plus integral controller. Proportional controller will produce a gain of Kp, integral controller will produce a gain of Ki, and one pole at origin. Now this is PI controller, this is output P of S, this is input E of S. So what is the PI controller transfer function? The PI controller transfer function is Laplace transformation of output by Laplace transformation of input, which is equal to Kp into S plus Ki by S. Now this is the PI controller transfer function. If you observe here, the PI controller will produce one pole at origin and one finite zero in the left hand side of S plane. One finite zero in the left hand side of S plane. Now this is the PI controller. Now we will see with the effect of PI controller. So what is the PI controller? The PI controller Kp into S plus Ki by S. So with PI controller, then what is the forward path gain? The open loop control system transfer function G of S, which is nothing but Kp into S plus Ki by S into S, S square into S plus 10. Now the type is 2. Now type is increased, therefore steady state error is decreases. This is already the same effect which we are observed in a single I controller also. Is it right or not? But what is the problem in the single I controller? Will affect the stability, but what happened here we will see. Now this is the steady state analysis behavior, and what about the transient state analysis? So what is the transient state analysis? Now the transient state analysis means now we want to find the characteristic equation. So the characteristic equation is 1 plus G of S is equal to 0, S square into S plus 10 plus Kp into S plus Ki equal to 0. Characteristic S cube plus 10S square plus Kp into S plus Ki equal to 0. This is the characteristic equation of order 3. So what is the internal quotient product? 10 into Kp. What is the external quotient product? 1 into Ki. These are the gains which we can able to control, because these are the gains which we can have a in our control. Therefore, this product should be greater than that. If this product is greater than that, definitely the closed loop control system is stable. So what is the PI controller finally? The PI controller is decreasing the steady state error without affecting the system stability. The PI controller will decrease the steady state error but without affecting the system stability. Okay, that is a advantage, complete advantage. There is no other disadvantage. Decrease the steady state error, no affect the stability. Improve the stability, no affect the error. This is the advantage of the combination of controllers. Okay, no doubt. So once if you finish this, then you try to identify what should be happening in this particular controller. Now this is the PI controller. Now, what are the key points? The PI controller decrease the steady state error without affecting stability. PI controller decreases the steady state error without affecting stability. PI controller decreases the steady state error without affecting stability. What is the transfer function? The transfer function of PI controller, is Kp plus Ki by S. Kp plus Ki by S. Now we'll see the practical circuit. See if you have any doubt, how practically pole, how practically zero, how Ki is changed, how Kp is changed, how Kd is changed. You can easily understand with the practical circuit, right? Now this is controller. This is controller and this is the inverter portion. To compensate that minus value, we'll take an inverter. Now this is the inverter portion, produces -1, and this is the controller portion. You just cross check. Which controller? PI controller. So what is this transfer function? Now if you see the transfer function, R2 plus 1 by SC2 by R2 plus 1 by SC2 plus R1, which is equal to 1 plus SC2 R2 by R1 SC2 plus R2 SC2 plus 1. SC2 cancel. Now see here. Now this is R1 SC2 plus 1 R2 SC2. Now if I divided, now this is the constant 1 plus SC2, 1 plus SC2, if it is cancelled. Now see here. Now this is the transfer function R1 SC. This is Kp plus Ki by S. Okay, then you compare with the original transfer function and you can easily have the Kp value and a Ka value. Okay, not on. What is this? No, this is not there. R2 plus 1 by SC2 by, this is Z2 by Z1, R2 by R1. This is only, sorry, this is R1. Okay, this is R. So what is this? This is nothing but 1 plus SC2 R2 by SC2 R1. Then you just simplify that circuit. So the transfer function is nothing but SC2 cancel, R2 by R1 plus 1 by S into 1 by R1 C2. But what is our transfer function? Kp. Our control transfer function is Kp plus 1 by S into Ki. Then you can easily apply the controller. So what is the controller constant? So now the controller constant Kp, which is equal to R2 by R1, and Ki, which is equal to 1 by R1 C2. Then you can change this value and you can get a different Kp and Kv values. And what is this? This is the practical circuit. Practical circuit of PI controller. Okay, note down. If you take after the combination, so even if you take after the combination, which will not give the complete advantage, only one advantage, no other disadvantage. Okay, so what I am doing is, now I want to improve both stability as well as error analysis. So therefore there is no only one option for us. So we want to club all the controllers what we have so far, right? So what we are doing now, we'll take proportional plus integral plus derivative controller, P plus I plus D controller, or simply called as PID controller. PID controller. Okay, so proportional plus integral plus derivative controller, or simply called as a PID controller. Now what is the transfer function? First you find the transfer function. What is the PID control transfer function? The PID control transfer function, the proportional control will produce a gain of Kp, plus integral control produce a gain of Ki, plus the proportional control will produce a gain of Kp, integral control will produce a gain of Ki by S, derivative control will produce a gain of Kd into S. Now this is the controller transfer function, this is the controller output. Now this is the controller input. That is the controller output and this is the controller input. Now what is the PID control transfer function? Now PID controller transfer function is the PID controller transfer function Laplace transformation of output by Laplace transformation of input, which is equal to kd into s square plus kp into s plus ki by s. This is the PID controller transfer function. So now this is the PID control transfer function. Now I'll take the same plan where error is more but system is stable. So now what happening we will see. Now with PID controller, now PID controller is nothing but here Kp plus Ki by S plus Kd into S. Now this is PID controller, right? Now see here. Now with PID controller, this is without plan. Now with PID controller, what is the open loop control system transfer function? Now the open loop control system transfer function G of S, which is equal to Kd into S square plus Kp into S plus Ki by S into S, S square into S plus 10. Now type equal to 2, type is same, steady state error will not disturb. Now what is the type here? Previously 1, now type is increased, now steady state error is decreased, because previously earlier type is 1, now the type is 2, decreases. Now this is the steady state analysis, error analysis, right? This is the steady state analysis. Now what about the transient state analysis? Now the transient state analysis is, we have to identify the characteristic equation. 1 plus G of S equal to 0, S square into S plus 10 plus Kp into S plus Kd into S square plus Ki equal to 0. Now S cube plus 10 plus Kd into S square plus Kp into S plus, now this is S cube, now this S square and this S square, 10 plus Kd into S square plus Kp into S plus Ki, which is equal to 0. This is the characteristic equation of order 3. Now see here, the internal product, what is internal product? 10 into Kd, 10 plus Kd into Kp is internal product. What is external one? 1 into Ki. Now the internal quotient product is greater than external quotient product. The internal quotient product is greater than the external quotient product. Closed loop control system is stable. The internal quotient product is greater than the external quotient product. Closed loop control system is stable, and it will become more stable because the internal quotient product is very, very high. When the internal quotient product is as much as strong, such that your system will become more stabilized. Now see the effect. The stable system will become more stable and error is decreased. Now you can get the two advantage. It will improve the steady state analysis as well as transient state analysis. Is it right or not? Now first you note down this. Now these are the controllers, how it will improve the transient state analysis as well as steady state analysis, and such that you can get the desired characteristics, right? right? Now we just recollect what is PID controller. What is the PID controller? PID controller will improve both transient state analysis as well as steady state analysis. Means it decreases the error and improve the system stability. Now, PID controller transfer function is KD into SS square plus KP into S plus KI by S. What is the meaning of that? Now, the PID controller will produce one pole at origin. The PID controller will produce one pole at origin and two finite zeros. The PID controller will produce one pole at origin and two finite zeros in the left hand side of S plane. The PID controller will produce one pole at origin and two finite zeros in the left hand side of S plane. Now see here, this is the PID controller. Now one pole at origin and two finite zeros. You know that generally when pole is added at origin, type is increased, error is decreases. When error decreases, stability is affected. That affected stability is compensated by first finite zero. Okay, the first finite zero is spend his time towards the compensation of affect the stability because of adding one pole at origin. So this job is decrease the steady state error but affect the stability. That stability effect is compensated by first finite zero. Now the second finite zero is free here to improve the system stability. Already system is stabilized and it will try to improve more stabilized. Okay, it is used for improve the system stability for further. Now this is the PID controller transfer function. Now let us check here, and in the root locus diagram also we just recollect what we are doing is if you take a transfer function and draw the root locus diagram, and in that root locus diagram the branches are moving towards the right hand side or it is on the right hand side. In such a transfer function, if you add 1 0, what happens? If you add 1 0, then that right hand sided branches is completely shifted to the left hand sided. Then there also we can write one point. You just go through and cross check. Now when we add 1 0 in the transfer function, then the root locus branches shifted from right hand side to left hand side, which means that the system stability is improved. Now that is the reason why in the PD controller a finite zero will improve the system stability. That is the reason why in the PID controller, now this is a two finite zeros definitely improve the system stability. That is the reason why in a PI controller one pole at origin and 1 0. Pole at origin is type increases, steady state error is decreases, but stability is affected. That effect is compensated by a finite zero in the left hand side of S plane like this. Okay. So now we'll see the practical circuit of PID controller. Now what is the practical circuit of PID controller? The practical circuit of PID controller is I just write directly in frequency domain. Okay, don't confuse. Now this is the controller portion, you know that. Now this is inverter, you know that. This portion is nothing but an inverter part. Now this portion is nothing but controller. Now what is the controller transfer function? Now the controller transfer function is R2 plus 1 by SC2 by R1 by 1 plus, because this is the parallel combination, 1 by SC1 R1. Now see here, which is nothing but finally 1 plus SC2 R2 into 1 plus SC1 R1 by SC2 R1. SC2 R1. Now which is equal to S square C1 C2 R1 R2 plus SC1 R1 plus SC2 R2, right? Now this is SC1 R1 and this is SC2 R2 and this is S square C1 C2 S by SC2 R1. So if you simplify this one, now finally the transfer function is SC2 C2 S is cancelled, R2 by R1, and here is also R1 cancel, plus C1 by C2 plus S here is cancel and C2 also cancel, R1 is also cancel, R2 C1 S, R2 C1 S. So you compare your original transfer function. This is the original transfer function, PID transfer function. What is this original transfer function? See here, Kp plus where is Ki by S? Yeah, and one more term is also missing here, 1 plus R2 C1 into S plus here 1 by SC2 R1. R2 by R1 plus C1 by C2 plus 1 by SC2 R1 plus R2 C1 into S. R2 C1 into S. Now this is Kp plus Ki by S plus Kd into S. Now what is Kp? Kp, which is equal to R2 by R1 plus C1 by C2. What is Kd? Kd is nothing but R2 C1. What is Ki? Ki, which is nothing but 1 by R2 C1. These are the constants. In practical circuit, these are the constants. Okay. So this is the PID controller will improve the both transient as well as steady state. This is the transfer function, one pole at origin, two finite zeros, and this is the overall the practical circuit, the practical circuit of PID controller. Okay, note down this. This is very, very important. And the problems is also based on this particular thing. And also you know that now this is the inverting amplifier I am taking. What is the transfer function? You know that. Now if this is the inverting amplifier, the transfer function V0 of S by Vi of S, which is equal to minus Z2 of S by Z1 of S. Inverting amplifier. Now if you see here, Z1 of S now this is Z2 of S, but now the input is given to non-inverting terminal. Now the input is given to non-inverting terminal. Now the transfer function V0 of S by Vi of S, which is equal to 1 plus Z2 of S by Z1 of S. Now this is the inverting amplifier. This is the non-inverting amplifier. Right, now this is the PID controller whose effect, okay, the PID controller effect is will improve both transient state as well as steady state, and it is a transfer function, and this is the practical circuit of PID controller, and these are the practical quotients. Okay, these are the practical quotients or practical constants or practical gains, how this Kp and Ka and Kd is changing, and this is useful. You know that this is the inverting amplifier, and because the input is given to inverting terminal, and this is the non-inverting amplifier because the input is given to non-inverting terminal, and these are the transfer functions. Okay, note down this.